Welcome to Study Loop.
Hi everyone, so what we have is air going through a compressor, and the compressor casing is cooled by liquid water. So the air comes into the compressor at 14.7 psia and a temperature of 520 degrees Fahrenheit, and leaves at a pressure of 150 psia. The cooling water is able to remove heat from the casing at a heat transfer rate of 10 BTU per pound mass. The compressor is being driven by a power of 700 horsepower, and the air has a volume flow rate of 5,000 cubic feet per minute. What we're asked to find is we're actually asked to find the exit temperature of the air while we vary this Q dot that is specified up here, the rate at which heat is pulled out of the compressor casing. So what we're going to do first is just go ahead and write our assumptions. We are going to assume that this is a steady state process, so things are not changing with time. We're going to assume that any changes in potential energy and kinetic energy are negligible, and we're also going to assume that air is acting as an ideal gas. So the first step that we're going to do is go ahead and identify our gas constant. So we know that we're dealing with air, and these are in English units, so our gas constant R for air is going to be equal to 0.3704 psia cubic feet all over pound mass Rankine. And by using the inlet temperature, we know to be equal to 60 degrees F. This translates into a Rankine temperature of 520 R, and this gives us an inlet enthalpy equal to 124.27 BTU per pound mass, and this will be equal to H1. Now what we can do is we can use the ideal gas law to solve for our specific volume, to solve for our mass flow rate. So we can say that specific volume 1 is equal to RT1 all over P1, which gives us a specific volume of 13.1 cubic feet per pound mass. And by using this quantity, we can solve for the m dot by saying that m dot is equal to the volume flow rate all over the specific volume. And we can plug these in, and gives us an m dot of 6.36 pound mass per second. Now we can use the conservation of energy to say that the total energy coming in is equal to the total energy leaving. This is because we're in a steady state system, so the system itself is not having any increase or decrease in energy. So what we can actually break this out into its constituents and say that E in is equal to the work coming in, the horsepower, the power of the compressor, plus the incoming mass with its enthalpy, is going to be equal to the heat that is removed plus the exiting mass with its enthalpy. So what we can say now is that work in minus Q dot out is equal to m dot H2 minus H1. Now remember, we are asked to solve for the exit temperature, and with the terms that we have here, one way we can solve for the exit temperature is to solve for our exiting enthalpy. So if we isolate our H2, we'll see that H2 is going to be equal to the work that comes in minus the heat that is pulled out all over m dot plus the incoming enthalpy, and that's equal to H2. So remember, we're asked to change our value of Q out, which is the heat that is being pulled out, and that is being changed from 0 to 100 BTU per pound mass. So what I went and did was I changed this quantity while keeping everything else constant, and that gives us values for H2. Now H2 can be directly correlated to a temperature, and what I did was I compared these H2 values with temperatures in the table 8-17E, and found a list of temperatures that these enthalpies corresponded to. Now this graph here shows our cooling rate on the x-axis that's changing from 0 to 100 BTU. And on our y-axis, we have the exiting temperature that is going from approximately negative 50 degrees to about 400 degrees Fahrenheit. And as you can see, as our cooling rate increases, our exit temperature decreases. And this makes sense because as our cooling rate goes up, we're able to pull more heat out of the gas that's leaving the compressor. Therefore, we see a decrease in exit temperature.